Hello there, welcome as we finish off our unit looking at the group 17 elements, the halogens. This lesson we're going to look at reactions and uses of the halogens, where our objective is to describe certain reactions of the halides and halogens and state some uses of halogens and their compounds. Learning outcomes were addressed in just below there. So in the previous video, we discussed some trends in the physical properties and looked at the trends that we observe in the reactivity of the halogens as you move down the group. We're going to start today a little bit different, talking about something that is called a qualitative analysis. A qualitative analysis is a kind of experiment, I suppose, where you are determining the chemical composition of a sample. So essentially, it's identifying the identity of an unknown substance as opposed to getting numerical values where a quantitative analysis where you might get a mass value or a concentration value or a volume value or something like that. You get numerical data. In a qualitative analysis, you're getting non-numerical data. You're getting information about the chemical composition of a sample. So it involves the identification of elements through a number of chemical tests. These could include changes in color, characteristic gas given off, precipitations that form, etc., etc. There's a whole bunch of things that could apply here. We're going to look at some quick tests you can do to identify if a halide is present, say if you had an unknown sample. So doing a qualitative analysis for a halide. A precipitate will form if the halide is dissolved in nitric acid and then you add silver nitrate. And you can then differentiate between if you've got chloride, bromide, or iodide ions by the addition of ammonia that we'll see in just a minute. So we can see here, if we have an unknown halide solution based on the precipitate that forms when we add nitric acid and silver nitrate, we could potentially identify what halide is present by the following observations that might be observed. So our chlorides, our bromides, and our iodides all form a precipitate when we dissolve in nitric acid and add silver nitrate. Now these are a very similar color to each other. We've got the chloride, which is a white precipitate, bromide is a cream precipitate, and iodide is this pale yellow precipitate. We can then do further tests to identify with more, I suppose, certainty which halide is going to be present based on what we observe when we add ammonia. So we first can add some dilute ammonia. If the white precipitate dissolves, this will be characteristic of the chloride halide. And we could deduce that if we've got the white precipitate with the silver nitrate and then it dissolves with dilute ammonia, we can narrow it down to being the chloride ion present. However, the bromide and the iodide will both remain insoluble, so dilute ammonia won't dissolve the precipitate that forms in these two instances. So you can then add additional concentrated ammonia, and if we see the dissolution of the precipitate then, we can deduce it's going to be bromide. If it remains insoluble in both of these instances, we can deduce that it is the iodide that is present. Now, the reason we get these differences in solubility all has to do with the fact that we form these different types of complex ions, depending if we've got the chloride, the bromide, or the iodide, and they're going to have different solubilities accordingly. But at this stage, all we need to know is that we do, in fact, see a difference in the solubility, and that will help us to identify which halide is present. For example, here's a question I want you to have a go at. Pause it now, see if you can puzzle an answer. What would be observed when silver nitrate is added to a solution of bromide ions? Write an equation representing this. How could you then identify it from the chloride or the iodide ions? So pause, consider this table, and see if you can answer the three parts of that question, and we will go through and answer now. So if we add silver nitrate to a solution of bromide ions, we would see a cream precipitate that would form. That's what we're told here. That's the qualitative analysis that would occur in this instance. Now we can have a silver nitrate aqueous plus the bromide ions aqueous. We get a displacement reaction where we form the silver bromide, which is a solid. Very important that it's solid there because that is implying that it's the precipitate. It's not soluble, so we form the precipitate and the nitrate ions. Now we can simplify this further to an ionic equation where we could just show the silver ions, which is in the silver nitrate, reacting with, in this case, our bromide ions, which is in the solution, and we form the silver bromide solid because it is the precipitate. How could we then go on to rule out that it's not a chloride or iodide? We could then do the addition of dilute ammonia and the addition of concentrated ammonia, and we would see dissolution upon addition of concentrated ammonia after it remains insoluble with the addition of dilute ammonia. And this will confirm that we have the bromide ions and not the chloride or the iodide. Let's look at some more reactions of the halides that we need to be familiar with. So when we're referring to the halides, we're referring to the ion of the halogen. For example, chlorine goes to chloride, bromine goes to bromide. The general name is the halide. Let's look at some reactions with sulfuric acid. Sulfuric acid with a chloride can be used to generate hydrogen chloride as a gas quite easily. You just add the sodium chloride to the sulfuric acid and we form that. However, we can't produce hydrogen bromide or hydrogen iodide the same way. And it's all to do with the strength of the sulfuric acid as an oxidizing agent, how good of an oxidizing agent it is, and also to do with the relative stability of the HBr and the HI. Because we said in a previous lesson, in the last lesson, we said that as we go down the group, it gets easier to decompose the halide, hydrogen halide, because that bond energy becomes weaker. So what we see when we add sulfuric acid with the bromide in the same way is that we'll first generate the HBr. However, the sulfuric acid is then a good enough oxidizing agent, and this is a weak bond that we can further decompose down into bromine gas, sulfur dioxide gas, and water. So we'll see that characteristic reddish brown color be given off when we release the bromine gas because the HBr is being further oxidized. Similarly with the HI, when we react the sulfuric acid with iodide, we produce the HI, but then through a number of different reactions, we end up with a number of different products where the HI gets oxidized. And similarly, we form sulfur, so we form yellow sulfur. We see the purple I2 gas, so that very characteristic purple color for the iodine, and that smelly hydrogen, dihydrogen sulfide gas let off as well. So we can produce HCl this way, but we can't produce HBr or HI this way due to the weaker bond energy going down the group, therefore easier to decompose them. The sulfuric acid is sufficient to oxidize them. Another reaction we need to be familiar with is what's called a disproportionation reaction. So we're going to look specifically at chlorine. Products of chlorine with sodium hydroxide is temperature dependent, and it's also an example of disproportionation. So there's two things we've got to take away from this section here. Firstly, the different products that we can form when we react chlorine with sodium hydroxide based on the temperature, but also the fact that these are both types of disproportionation reactions. What does this mean, you ask? Well, it's a type of redox reaction where the same species is both oxidized and reduced. Let's look at an example of this. First, we have to be familiar with the chlorine in cold alkali, so at about 15 degrees Celsius. What we observe is this reaction here. We've got the chlorine reacting with sodium hydroxide. We form the sodium chloride. We form this sodium chlorate, chlorate 1, we'll see why that is in just a second, and we form water. Now, what I want you to do is write this reaction out, and then I want you to do oxidation numbers for all of the elements present and use these oxidation numbers to show that the same species is being both oxidized and both reduced. See if you can do that one, and then we will check the answer now. So we have 0 for our neutral diatomic chlorine, +1 for the sodium, -2 for the oxygen, +1 for the hydrogen, +1 for the sodium, group 1, -1 for the chlorine, +1 for the sodium, -2 for the oxygen. But then what we have is we actually have a +1 for the chlorine there in order to get that neutral. Over here we have +1 and we have -2. So let's have a look. Let's show this disproportionation reaction because we have the change in oxidation number. Our sodium isn't changing, our oxygen isn't changing, our hydrogen isn't changing. What's happening is our chlorine is going to -1, so it's getting more negative, so it's being reduced. Reduction is gain. But we also see the chlorine going to a +1. So in this case, it's getting more positive, so it's also undergoing oxidation. So we can show the disproportionation reaction because we have the change in oxidation numbers both showing one chlorine getting reduced, one chlorine being oxidized. So we have the same species being both oxidized and reduced. Here's another reaction that we can get. The same reactants, only if we have hot alkali, so 70 degrees Celsius, we see a slightly different formation of the products. In this case, we form the sodium chlorate 5. Well, let's discuss first of all why this is called sodium chlorate 1. It's because we have the chlorine in the +1 oxidation state. If this is called sodium chlorite 5, you might be able to puzzle out, just based on that name, what oxidation state the chlorine is going to be in. But why don't you have another practice of this in case you didn't quite get it that first time? Can you pause and use oxidation numbers to illustrate the oxidation and reduction reactions that are occurring in this disproportionation reaction? So do the exact same thing and then check the answer now. So let's do the same thing that we did before. Let's just focus on the chlorine though, because we know this is a disproportionation reaction. So let's see the oxidation numbers. Let's start with a 0 over there. It's going to be -1 over here. So straight away we can see that we have our reduction. We're getting more negative, we're gaining electrons. This one over here, we have the sodium +1, oxygen's -2, but we've got 3 of them. 3 times -2 is -6, +1, therefore it has to be +5 over here in order to get that to be neutral because it doesn't have a charge. And we observe the same thing. We have a positive change in the oxidation number, therefore it's losing electrons, therefore it's undergoing oxidation. So we need to be familiar with both the products of these two, just slightly different reaction conditions. We form sodium chloride. I mean, the products are the same. We just have a different sodium chlorate 1 for the cold, sodium chlorate 5 for the hot. And then we want to use oxidation numbers in order to demonstrate this as a disproportionation reaction. Finally, to finish off the unit on the halogens, let's just discuss briefly some uses of these halogens. Like I've said before, it's good to zoom out from just an academic standpoint to see how we can apply this knowledge and apply these chemicals and these compounds and these elements, etc., to a broader application in our lives. Halogens have numerous and useful purposes: sanitation, pharmaceuticals, formation of plastics such as PVC, pulp and paper, halogenated hydrocarbons as solvents, refrigerants, and in aerosols. 2 that we need to be specifically aware of is first, it's an important step using a halogen chlorination, so using chlorine in water purification. Because what this does is this kills potentially harmful bacteria that gives us delicious, clean drinking water that doesn't make us sick. And we see a disproportionation reaction occur here as well, where we have the chlorination, we add the chlorine to the water, and we form these 2 species. One of which is the chloric acid, and this is theorized to produce the reactive oxygen atoms that can kill the bacteria. So we could see this as a disproportionation. We got 0 on the chlorine there, -1 on the chlorine there, +1 on the chlorine over there. The same species has been both reduced and oxidized. Final one we've got to be very familiar with is the idea of bleach. This is important for numerous household and industrial purposes, such as getting colors out of things or killing germs. What it is, it's a mixture of equal sodium chloride and sodium chlorate 1. We just saw the sodium chlorate 1. Pause, see how much you remembered from that previous slide. What are the reaction conditions to form the sodium chlorate 1? Answer it without going back maybe. It is in fact the cold alkali, not the warm alkali. The hot alkali gives us sodium chlorate 5. The cold alkali gives us sodium chlorate 1. Our bleach is just a mixture of sodium chloride and this sodium chlorate. And that is the end of not only the lesson, but another unit. What have we done? We've described and explained the reactions of halide ions with aqueous silver ions followed by aqueous ammonia and concentrated sulfuric acid. We've described and interpreted in terms of changes in oxidation number the reaction of chlorine with cold and hot aqueous sodium hydroxide and recognize this as a disproportionation reaction. We explained the use of chlorine in water and stated the industrial importance and environmental significance of the halogens and their compounds. Here are the tasks to consolidate your understandings for this lesson. Pause and work through those. Thank you very much. I will see you next time as we start a new unit. Have a great day.